In this video, I'll show you how to fit a conditional latent growth model with both time invariant and time varying covariates. So in this step, we assume that we already fit the unconditional latent growth model first. So you should always start with the unconditional model. If the unconditional model fits well, then you can proceed with adding covariates. Okay. So, this is the example for the Humana-Taylor paper. The growth trajectory of interest is of ethnic identity exploration. So in this first line here, we have the measurement model, which is with the unconditional latent growth model for ethnic identity exploration. So I have here intercept and slope measured by the 5 waves of ethnic identity exploration. So I and S are the latent factors. So I can add time invariant predictors and time varying predictors. Here the time invariant predictors are age and net, which is where they are from, if they are Mexican or American. So I'm using these two as predictors of the intercepted slope. So I just do I, S, age, and net. That's how we typically add time invariant predictors in a latent growth model. Now, for time invariant predictors, we have ethnic identity, resolution here, and the measured in 5 waves, just like ethnic identity exploration. So in this line, I have ethnic identity exploration 1 regressed on ethnic identity resolution 1. And then the second line, ethnic identity exploration time 2 regressed on ethnic identity resolution time 2, and so on. Okay, so that's this part here is how you add time varying predictor in a latent growth model. I will run this. Let's see the results. So first thing is model fit. So the chi-square is not significant, meaning that this model has exact fit. The root mean squared error is of approximation is 0.04, and it's not statistically significant, showing evidence of close fit. The CFI is 0.97, TLI is 0.96, also showing evidence of close fit, and the SRMR is 0.093, which also is consistent with close fit. Okay, now going down to the results. Here we will focus on the standardized results because we want to look at the regression coefficient. So we skip the standardized. So the standardized result shows that both age and the country of origin have a significant effect on the intercept. So in this case, back here to the code, just to so net is nativity, coded as 0, 1. So age is continuous, so an increase in 1 standard deviation of age corresponds to this increase, but we can't interpret this because it's not statistically significant, right? We can interpret net because net is statistically significant, and it shows that the difference between the two groups is minus 2.621. I don't remember which group is coded 1 here, but the the group that's coded 1 is smaller in terms of nativity as with respect to the intercept, um, then the group code is 0. Now, there is, for the slope, there is no effect of age or nativity on the slope because both coefficients here are not statistically significant. Then, so this is for the time invariant covariates. Now let's look for time varying covariate. We find that ethnic identity resolution has a significant relationship with ethnic identity exploration at each time point. Not only that, but the coefficients about the unstandardized coefficients about the same. Now let me go to standardized here. They still about the same. And you can see here that one standard deviation change in ethnic identity resolution at time 1 corresponds to expected 0.42 standard deviation change in ethnic identity exploration. And that is pretty similar across each time point. I could fit an alternative model where I put constraints on these effects so they are the same across time, and then do a chi-square difference between that model and this model to test the hypothesis that the relationship between ethnic identity resolution and ethnic identity exploration is constant across time. Here what I have is a residual correlation. So the residual correlation between the intercept and slope is minus 0.42. It's statistically significant. That is fairly common. It's once you add predictors of intercept and slope, that typically does not account completely for the correlation between intercept and slope. So this type of models typically have a residual correlation between intercept and slope, and that's fine. Okay, and then we can look at, scroll down here past all the standard solutions and look at the I-squared, and they are fairly high. But also the I-squared for intercept and slope is how much variance the two time invariant covariates explain of the intercept and slope, and those are low because there were no, for the intercept there was just one significant coefficient, for the slope there was no significant coefficient. So that's how you run a linear growth model with time varying and time invariant predictors.